So back in 1991, there was this big volcanic eruption in Mount Pinatubo, and it injected a whole load of gases and ash into the atmosphere. And actually, it was so explosive that those gases and ash were injected into the stratosphere. So that's like the sort of outer part of the atmosphere. And it kind of ranges between sort of 10 to 20 kilometers above the surface, depending on where you are in the planet. So pretty high up. And one of the main components of that eruption was sulfur dioxide, or SO2. And when SO2 oxidizes in the atmosphere, it becomes this really reflective aerosol. So this particle suspended in the atmosphere. And so it was reflecting all of the sunlight back to space. And what we saw after that eruption was about a period of 1 or 2 years of global cooling by about 0.5 degree. So it was just one injection of SO2 from this volcano, and it caused the whole planet to have a global average reduction of about 0.5 degree. But it only lasted for about a year or so, because the aerosols that get injected into the atmosphere fall out after a few months to a year. So this kind of then propelled the idea of stratospheric aerosol injection to intervene into the climate system to reduce the rising temperatures. So unlike a volcanic eruption, rather than having this one single injection of SO2, we would have a continuous injection into the stratosphere over a period of years, depending on what your scenario is and how long it takes to remove carbon dioxide from the atmosphere. And this is just an example of a strategy that you might use. And then the aerosol cloud that forms from that sulfur dioxide that I mentioned, this is just like an example of how that might be distributed across the stratosphere. But that would reflect sunlight back to space and then cool the surface of the planet. And that's what that final plot is showing there. So obviously, we kind of know that it works from volcanic eruptions. And there are lots of potential benefits of stratospheric aerosol injection. It can reduce heat waves and floods and droughts. It can reduce sea ice melting. And on the right-hand side here is just an example of some extreme heat. So this plot on the left is like a greenhouse gas, high emissions scenario. On the right-hand side, it's that same scenario, but with stratospheric aerosol injection on top of it. And it's just the number of days in a year that you'd experience really extreme heat overnight. And you can see that we just don't have as many of those nights with SAI. But that's obviously not the full story. As you've already heard, there are quite a lot of uncertainties associated with stratospheric aerosol injection. So you have the physical uncertainties of different patterns of surface cooling, precipitation patterns can shift. We might see ozone depletion in the stratosphere because we're sort of adding things into the stratosphere. It could be warming in the stratosphere, which could change large-scale circulation. But there are also modelling uncertainties. So the baseline scenario we choose to model from, so that greenhouse gas emissions scenario, that makes a difference. Our target temperature, like what temperature do we want the world to be, and how that might change in terms of how much you have to inject. So there are lots of modelling uncertainties.